Okay, so we're about to start our last session, but before we do that, first of all, if you were paying attention closely, our last talk was by Manus Visser, not Rob Myers. So Manus graciously agreed to fill in at the last minute because Rob missed a flight in Tokyo and wasn't able to make it here, or missed a connection there. But this, I think, was going to be the first slide of Rob Meyer's talk. So he sent this over to us. So we're displaying it for your viewing pleasure here.
Website? Yeah.
What?
You put it on the website. Yeah.
Sure, we'll put it on the website somewhere, whatever website it is. Okay, and the last thing before we get started, we just wanted to take this moment to extend a thank you to Carly Barrett. They have been incredibly helpful in organizing this conference. Basically, anytime I needed to have something done, I send an email and it was done within usually an hour or less. So they've taken care of all of the snacks that we've had, the hotel reservations, lots to do with the banquet tonight. So yeah, we got a small gift. So thank you very much, and let's get a round of applause. We'll do that after this. Okay. Okay, and then who's our chair? Okay, and I'll hand it over to our chair.
Okay, so our next speaker is Bob, who was originally told that he has 1 hour and 15 minutes, but he actually has 45.
Yeah.
So now it's my task to stop him.
I'm going to take the hour and 15, and you can reduce the time of the next speaker if you need to, if you need to end on time. I think Rob Myers was going to give a much more interesting talk than I'm going to give, based on that first slide. So first, I'm really pleased to be here to help give Ted a little bit of the recognition that he very much deserves. One thing, though, when the chairman spoke at the opening of this conference, he was, talking about Ted's longevity here and so on. And I was a postdoc here from 72 to 74. Ted is a newcomer. I mean, he's just getting started here and just breaking in. So I really did not have any idea what the chairman was talking about. Okay, what I'm going to be telling you, and I have to figure out which, I don't want to explode this. Yeah, okay, that's the pointer button. The real title of my talk is Black Holes Are Watching You, but I don't like to advertise that because it brings in a very large audience when I give that as the title. And I'll be telling you about, what started out as just a cute project, joining this group from Vienna, and then became, with the very close collaboration of now my two former students, Dane Danielson and Gautam Sadaschandran, into a significant project. There's actually more, one published paper and some more work in progress on this topic, but what I'll be telling you about is mostly what's in these two papers, if you want to get any more detail on this. So what I'm going to be talking about is decoherence phenomena, which is, familiar in many contexts to many people, certainly familiar to experimentalists who are trying to do quantum experiments and don't want to, or building quantum computers or whatever, and don't want decoherence to occur. I mean, entanglement between the quantum system you're interested in and other things in the environment will cause the system to, or cause the environment to react differently depending on the state of the system, which will result in quantum entanglement, which will result then in decoherence of the system. That's, again, familiar in many contexts. What I'm going to be telling you or trying to explain in this talk is that black holes, the presence of a black hole, of course, it has to be reasonably near if it's going to have a big effect, in a sort of fundamental way, decoheres any quantum system. It does it effectively by watching the system. I'll explain that. And it watches the system essentially by harvesting information about any long-range fields of the system, particularly electromagnetic and universally gravitational fields of the quantum system. And again, one of the things I find remarkable in this is that it admits a very simple and precise description. But to get started, I don't want to have a black hole around and want to begin to get us thinking in the right direction with a really neat Gedanken experiment that was originally proposed by Mari, De Palma, and Giovanetti, which gives rise to an intriguing apparent paradox. So there are two experimentalists in this, and in quantum experiments, it's traditional and unfortunately being used in this case to give them the names Alice and Bob. But Bob is not me and not any relation to me. So don't make that association, especially when he'll end up in a black hole in a couple of slides from now. That's not me. Okay, so the idea here is, there's both a charged and massive gravitational version. It's more familiar and simpler to just talk about the charged version. The gravitational version has a slight twist to it too that I'll get to later when I explain the slight differences in the gravitational case. But Alice has some massive, well, let's make it a charged particle, I just said, that is put in a quantum superposition. And a nice simple way of doing that is imagine that Alice's charged particle has spin. It was put through a Stern-Gerlach apparatus and the spin was initially out of the board in the x direction, and it's put into a z superposition. This is a space-time diagram. Z is this way, forward in time is upward, of spin up and spin down. And she's going to eventually recombine the superposition. The separation was done in the distant past, so I haven't shown it here. And she's going to test for coherence by seeing if the spin returns to pure X spin when she brings these two superposed components together. And if there was no decoherence, the spin would be in the X direction when she brings it together. Okay, the complication in this experiment is that we have this other unrelated experimentalist, Bob, who is going to try to figure out which path Alice's particle is in by releasing a charged particle from the trap and seeing how much Coulomb attraction there is. Because if Alice's particle was here and spin down, it's closer to Bob and there's a stronger Coulomb field, and if and a weaker one if it was spin up. So Bob can get some which path information. Now, if Bob had a classical particle or something, he could presumably get complete information. He has a quantum particle, so he's probably not going to get complete information, but he's certainly going to get partial information. But if Bob gets which path information, his particle must be entangled in some way with Alice's, and Alice's particle can't be decohered. The final twist in this Gedanken experiment is shown with these dotted lines, which are light cones or null planes, perhaps, it doesn't matter. What this is showing is that we're going to ask Alice to do her recombination and Bob to do his releasing and measuring where his particle is. We're going to have them do that space-like separated from each other. And that means by causality, what Bob does can't influence Alice's decoherence or anything like that. So if we ask the question, is Alice's particle decohered? One answer is yes, it must be, because Bob could get some which path information. But the other answer, which is not revealed in that slide, so that was okay that my thumb hit the wrong button. The other answer is Bob couldn't influence Alice, so why shouldn't her particle be completely coherent, and therefore she'll get spin up? I mean, this is a well-defined experimental question. So those of you in the audience who have not heard a talk by me or my collaborators before, or read our papers or whatever, if you want to try to answer the question, will Alice's particle maintain coherence? Feel free to do so, because if it's obvious, I can speed up the rest of the talk. Otherwise, I will have to take the extra half hour. Well, the answer is that Alice's particle indeed will be somewhat decoherent. How much depends on the circumstances, but it will have to be at least as decoherent as you would deduce from Bob getting information. But of course, what Bob does can't have any influence on Alice. And how is that? I mean, because Bob is just measuring Coulomb fields and so on. Well, the answer is there will be radiation from Alice in this process, and that will cause decoherence. Now, that is actually quite a, well, confusing or interesting thing, because there isn't a clean separation at any finite time between what is Coulomb field of Alice's particle, which is not an independent degree of freedom, and what is radiation, which is an independent degree of freedom and capable of causing decoherence. But if we go into the asymptotic future, the separation between radiation and Coulomb field becomes completely clean. The radiation goes out to null infinity. The Coulomb field follows the particle to time-like infinity, and they're completely cleanly separated. But if we imagine that Alice's particle is recombined and stays static forever, we can transfer that decomposition down to this finite time. And then if I choose a time slice that does what I've indicated here, you can interpret the entire electromagnetic field minus a common Coulomb field as being pure radiation, and Bob just measuring that radiation, which is completely irrelevant to anything. It's the radiation that has decohered Alice's particle. That's kind of interesting, because if you draw this time slice, then Bob is purely measuring the Coulomb field, and those are completely equivalent viewpoints. But anyway, moving on now to the black hole case. Well, I've drawn a conformal diagram here that includes a black hole, but if you ignore the black hole formed by gravitational collapse here, what I've drawn is the same Alice experiment as I showed before, except now that I have a conformal diagram and infinite time compressed onto the picture, I can even show the separation of Alice's particle. she holds it apart for a long time and then brings it back together, as I previously showed. And I want to ask if it's decohered. Well, the decoherence here is kind of forced because of the space-like separation from Bob in this Gedanken experiment. Alice only has a small amount of time. She's got to bring the particle back together quickly. That gives a minimum amount of radiation. But here, we're going to allow Alice to take as much time as she likes. And you'd think that would eliminate the radiation. But the twist here is that we're going to have Bob do the measurement from a black hole. And then there's no time limitation here. Well, there is a time limitation because Bob is going to fall into the singularity, but we can have a sequence of Bobs. And if you keep this, each Bob can get some which path information. If you keep the superposition open long enough, you can get an arbitrary amount of which path information from observations within the black hole. A key point is that the Coulomb field of Alice's particle perfectly well penetrates inside the black hole, and the which path information is available here. So that brings back now the same sort of paradox, except by doing this slowly, you can get the radiation to infinity as small as you like. So there must be some decoherence going on, because Bob can get, or a sequence of Bobs can get arbitrarily good which path information now if T is large enough, but the experimentalists inside the black hole can't be causing the decoherence. So I've just argued that the black hole itself must, in some sense, be causing the decoherence. And that's what I'm going to be explaining in the rest of the talk. So I think this is stuff I've already said, that you can get arbitrarily good which path information. The black hole itself must be harvesting the which path information. And I'll explain how. But let's first be a little, write down, well, if not an equation, a few, bras and kets, or kets in this case, symbols to indicate, okay. If, think, yeah, you can probably do better from the console than I would do hitting another button. Okay, good. Okay, back in this original Gedanken experiment, I already explained in words, we don't, there's no more role for this, not even relative Bob here in the rest of the talk. It's Alice and the radiation, and that will be the case. So just going back to the flat space-time version, if we look at what's happening in the asymptotic future, we have this as the joint state of Alice's particle and the radiation in the future. There is the spin-up case. Alice's spatial wave function is the same now because she's recombined, but that's tensored with radiation corresponding to the spin-up path, and there's the spin down and the radiation at infinity corresponding to that case. And since these radiation states will, in general, be different, Alice's particle will be decohered, and they'll be decohered precisely by the, the failure of psi1 to coincide with psi2. So if psi1 and psi2 are orthogonal to each other, the Alice's spin up and spin down states will be completely decohered. If not completely orthogonal, they'll be decohered by that sort of measure. Okay, so now what's the difference in the black hole case? Well, the difference in the black hole case is that the radiation that is emitted in this process does not need to go to null infinity. It could also go into the black hole. So the final state will have this extra factor of the radiation state through the horizon. We'll have to describe that quantum radiation state shortly, but we have other things that I'll have to do first, so we'll return to that. Now, if Alice does the recombination very slowly, she can indeed, as I already indicated, make these states at null infinity essentially the vacuum. I mean, keep the radiation to infinity, make that as small as you like. What I'm going to show you is that she can't make the radiation into the black hole as small as she likes. And the reason she can't is mathematically very closely related, well, to the memory effect in infrared divergences, but now relative to the black hole horizon, not relative to infinity in 4 dimensions as people encounter it in quantum field theory. Okay, so what we have to do now to proceed further is first describe the electromagnetic radiation through the horizon, describe that even just classically to begin with. So we'll start with that, then look at the quantum description and what happens in terms of orthogonality of the radiation states, because it's, you know, if the phi 1 and phi 2 become nearly orthogonal, that will completely decohere Alice, even if Alice's particle, even if she hasn't radiated anything to infinity. Okay, so I'm going to call n is going to be the normal to the horizon. I'm going to call the field tensor dotted into n the electric field. And the radial part of the electric field, I'm going to, we're going to sort of treat each component of Alice's superposition like it were a point charge. I mean, the finite size wouldn't be terribly relevant, as and I'm assuming that the components are well separated, although the separation will be small compared to the black hole parameters and the distance from the black hole. But to start with, let's just see what the characteristics of a point charge solution are. The radiation is described fully by the pullback of the electric field to the horizon, and the quantization on the horizon will all just involve this pullback of the electric field. So this would normally be referred to as the angular components of the electric field on the horizon. The transverse component, which I'll call the radial electric field, however, will not be 0 on the horizon for a point charge. So I should have said first, the tangential components, the angular components will be. If you have a static point charge, that's not going to be radiating anything into the black hole, but the Coulomb field of that static point charge will perfectly well penetrate transversely through the black hole, and this radial electric field will be non-zero. Okay, so now the key thing to understand is what happens if that's the static point charge, but what happens if I move a point charge to a new location. Well, Maxwell's equations will tell you that it will have to radiate a bit because if I move it to a new location, transversally or radially, it doesn't matter, that will change the radial component of the electric field on the horizon. But the divergence of E Maxwell equation tells you that if there's a time derivative of the radial component, that has to provide some angular components. Okay, but what's really important about this equation is what happens if I integrate over all time. And suppose I start with a point charge in one position and move it to another position. If I integrate this equation over all time, I'm going to get the difference of the radial electric fields. That tells you that the integral of the angular components of the electric field is non-zero, and indeed, that's completely not independent of how I moved the charge, how slowly or quickly I moved it from one position to another. This integral of the divergence of the electric field will be non-zero, and correspondingly, the integral of the angular components of the electric field will be non-zero. We'll see shortly why that's very important and key to the whole situation. But before I do that, I have to explain how we compute the quantum state of the radiation through the horizon and the orthogonality of two quantum states. So first of all, if we move the charge very slowly, the energy flux into the black hole will be given by electric field squared, and that we can make as small as we like. But we can't, I just showed you, we can't make the integral of one factor of the electric field small. Okay, so how do we describe the quantum state of the radiation? Well, we have to start with what the state of the radiation is without the charge and without moving the charge. And that would be, if you had a black hole formed by gravitational collapse, that would be well described by the Unruh vacuum. I'm going to approximate that as the Hartle-Hawking vacuum, which is an excellent approximation at low frequencies. And this is just for simplicity. And in the Hartle-Hawking vacuum, an excitation, a one particle excitation above the vacuum corresponds to a solution that's purely positive frequency with respect to affine parameter as the time variable on the horizon. Okay, so if we have a charge current source that we can treat as classical, that will perturb the Unruh or Hartle-Hawking vacuum state to be a state lying above the vacuum via a coherent state corresponding to the classical retarded solution. And the expected number of particles of quanta in this coherent state is just going to be given by the Klein-Gordon norm. Is just going to be proportional to the Klein-Gordon norm of this classical solution. We get the Klein-Gordon norm by taking the Fourier transform of the vector potential on the horizon, squaring that, multiplying it by omega, and integrating over the positive frequencies. So we take the positive frequency part and we apply a formula that should look familiar as textbook type Klein-Gordon norm. So this involves the vector potential, but now the electric field, I'm going to, the electric field is just going to be given by the time derivative of this vector potential. And this fact that I was making a big fuss of, that the integral of this is not zero, implies that this a doesn't return to its initial value. Why is that important? Well, if you have a function, I have a picture of this. We have a function that, let's say, starts from zero. I can choose a gauge where it starts from zero, and does not return back to zero. If you take its Fourier transform, you'll get a 1 over omega infrared type divergence at low frequencies. So that's going to get squared. I'm not concerned with ultraviolet properties, which will all be fine. I'm concerned with infrared properties here. The 1 over omega will get squared. It'll get multiplied by an omega, but then integrated, and that's going to give rise to a logarithmic divergence. So what am I saying to put things together? I'm considering a situation where we have a black hole. I have a point charge, which has been held here forever. Now I take it and move it over to here and hold it here forever. Right? This is a toy problem that we'll get back to what happens with Alice's experiment. But once we understand this, we'll be able to figure that out. I move it from here to here and I hold it there forever. How many photons are radiated into the black hole? The answer is infinitely many. And the infinity is all concentrated at these near zero frequencies. And well, I've already hinted that this should sound familiar from quantum field theory texts because, well, it's a special property at 4 dimensions in the quantum field theory case, and it results not from a change in position, but a change in momentum in the flat space quantum field theory case. But this is an exact analog of the infrared divergences that occur in scattering theory. It's exactly mathematically the same phenomena, and it's similarly directly related to the classical memory effect that you have, well, in basically any massless theory in Minkowski space in 4 dimensions, but in the black hole case, doesn't matter how many dimensions you're in or any other details. Okay, so this moving from one place to another radiates infinitely many soft photons. We might, well, for making estimates of how big n is when we don't do this for an infinite amount of time, it's useful to get this offset that we get from zero when we've moved a charge from one spot to another. And that's very easy to estimate using precisely Coulomb's law, because the size of the radial electric field is roughly the charge over some distance to the black hole. And if you move it in any direction, a distance d that's small compared to your distance from the black hole, that will give you this sort of dipole-like formula for the difference of the radial electric fields, which if you then, using Maxwell's equations and doing the V integral, convert that to a change in the magnitude of A, you get this estimate of going, I've set G, H bar, and C, well, yeah, G didn't come into this, but actually, I guess it does in terms of the radius of the size of the black hole. I've set G, H bar, and C equal to 1, and it'll go like the mass squared of the black hole times the charge times the distance you moved it divided by the distance cubed from the black hole. Okay, so now getting back closer to Alice's experiment, where she separates the particle into two components by a distance d and then brings it back together, is essentially the analog of moving a point charge to another position, holding it there for some length of time, and then bringing it back. And when Alice recombines her particle, she's going to cut off this, what would have been infrared divergence, and make it finite. That the number of, so if we go back to the point charge example, if I take the point charge, move it over here, hold it here for a long time, and then move it back, now the number of photons radiated into the black hole is not infinite. It varies as log v. Now, logarithmic increases in time are not that huge. Well, if you put in the estimate I just gave you, that gives you this times log v. But v is the affine time that you've held the particle open. Affine time is related to killing time by this exponential formula, and the killing time, is up to the redshift factor, the proper time in Alice's lab. So if I assume her lab is reasonably far from the black hole, so the redshift factor is of order 1, the t is giving the proper time in Alice's lab. And that means this logarithmic dependence on time actually is a linear dependence on time in Alice's lab. So the number of, if she does this experiment, the number of photons that she emits into the black hole is going to be given by this formula. And by doing it slowly, she does not stop the radiation from going on. In fact, doing it very slowly, she guarantees that there's going to be a lot of radiation going into the black hole. So that, in fact, is all we need to estimate the decoherence that's caused by the black hole. So let's go back to Alice's experiment to nail that down. So again, her experiment consists of putting the particle in a spatial superposition, keeping it in that superposition for a proper time t, and then bringing it back. This, the formula I just gave then estimates how many entangling soft photons are going to be emitted into the black hole. And if more than one of these such photons are sent into the black hole, the radiation, the two different radiation states will be essentially orthogonal, and her particle will be completely decohered.
What is essentially?
I'm sorry.
The essentially. What does that mean?
Well, the inner product will be e to the minus n. There might be a numerical factor of 2 or something that I'm missing, but e to the minus n. So like if n is 10, then it really is essentially orthogonal. Okay. So that gives an estimate then of how much time Alice has to do her experiment in the presence of a black hole to cause a decoherence. Well, if we're talking about the sun being a black hole, so we're an AU from it and we have something the mass of the sun, then even if she has an electronic, a charge equal to the electronic charge separated by a meter, which would be pretty difficult thing to hold in a superposition for any length of time, it will take 10 to the 43 years before the sun as a black hole would have decohered her superposition. But if she's very close to the black hole, this corresponding time is not quite as ridiculously small. Okay, I mentioned that the same things hold in the gravitational case. In fact, it's quite remarkable how much in parallel you can do the derivation with electric part of Weyl tensor replacing electric field, and these formulas that I won't go through here replacing the ones that I have. There is one little twist to it in that doing the separation will not actually cause there to be a dipole-like effect of the two components as one might imagine. But, well, at least if we were doing this in Minkowski space-time, there's a strict then conservation of center of mass. So if one of her components goes this way, the lab will go that way in such a way as to cancel the gravitational dipole moment. That's why gravitational radiation in the slow motion limit starts out at quadrupole rather than dipole. It's the same effect. So that actually, we only get an effect from the effective quadrupole that's produced by her superposition. So the decoherence time when you do the numerical estimate, again with the same black hole where the sun is of the mass of the sun, well, you see here I just get a decoherence of 10 microseconds in the gravitational case. That's a very big effect, but that's a very big effect if we were able to put the Earth in a coherent superposition with itself separated by an Earth radius. So if you manage to get the Earth through a Stern-Gerlach or other apparatus and keep it coherent, the sun as a black hole would decohere it in 10 microseconds. In other examples, it'll be a lot weaker an effect than we got in this other case.
Put in a grant or
Well, yeah. I mean, I think in the current environment, that might be the one that gets funded. So I might try it. Okay, I am running out of time, so let me not say a lot more, but if you look at what was used in the derivation, it really was just I didn't use anything really about the event horizon other than it was a killing horizon, and you'd get the same effects with an accelerating lab from the Rindler horizon or de Sitter space-time with the cosmological horizon. I put the de Sitter decoherence times here as formulas, and I'll just conclude that black holes really do have the ability to decohere quantum superpositions, and they do that by watching you and harvesting the soft gravitons and photons that have been emitted by your possibly very slow separation processes. And if you give a black hole enough time, it will decohere any quantum superposition. I think I've also made clear that experimentalists don't have to worry about doing some black hole shielding now of their experiments. It'll be not something of practical importance, but I think it is something to ponder in terms of the nature of black holes in quantum gravity and their whole relationship to phenomena in quantum theory. Okay, thank you.
Okay, thanks, Bob. Questions?
Yeah.
Thank you. Thanks for the talk. There's this paper by Maldacena and Biggs showing that you can also think of the same effect, the decoherence is just coming from Hawking radiation coming out of the black hole. How do you understand the relationship between the perspective where Alice is radiating soft photons to the horizon and the radiation coming out of the black hole itself?
Okay, this is actually, so, okay, there are a couple of things. Okay, this paper, which I didn't talk about, gives a kind of local in Alice's lab description of what's going on in this decoherence, and there's more to be said about that as well. So where you can actually see that what's relevant is the 2-point in the electromagnetic case, the 2-point function of the electromagnetic field along Alice's world line. And that is, the kind of very low frequency Hawking radiation can be, thought of, and the Hawking radiation associated with these sort of white hole modes that you don't have any analogs of in Minkowski space-time. So in a low temperature thermal bath in Minkowski space-time, you would not get any effect of this sort. Anyway, you can see that explicitly coming in. So now Maldacena and Biggs were looking at matter models that effectively produce the same kind of 2-point function. And they argued that in the electromagnetic case, given particular, dependence of conductivity on frequency, it would not be difficult to mock up the black hole response. In the gravitational case, I think there may be some serious difficulties in being able to mock up, both the temperature and the decoherence effects. But anyway, that, so this kind of decoherence is not completely unique to black holes, I think is maybe the main thing you were asking me about. And and that is indeed the case. You could mock up matter systems that are,
could you say something about what the relationship between the 2-point function on Alice's world line and the soft photons produced by Alice are?
Well, the source on Alice's world line, is, never mind 2-point function at first, is what's, producing the radiation. So through the retarded Green's function, that the current on Alice's world line, or the effective dipole, is really what we care about, because it's the difference between the two sources and the difference between the two radiation states that's important. So the current is directly related through the retarded Green's function, or the, better yet, the advanced minus retarded solution. And the 2-point function then on Alice of the current correlation function is related to the 2-point function, on the horizon, which in turn is related to the, to the norm of the radiation going into the horizon. I'm not explaining that terribly clearly, but that should give you some idea. The details really are in this paper of how you could relate the norm of the difference of the radiation on the horizon to 2-point functions on the world line.
Okay, thanks.
Other questions?
Hello? Yeah. You were mentioning there's IR divergence that showed up was the analog of what happens at scry in 4 dimensions. I'm curious if people have seen that in other types of experiments, like additional IR divergences you would have for scattering.
Well, this
off
is
of
not
a Schwarzschild
additional.
black hole.
This is the plain old standard IR divergences.
Yeah, I'm just saying, like, say a higher dimensional black hole, have people seen issues with the scattering in a black hole background that would similar how you see IR divergences in 4 dimensions? That makes sense.
Uh,
I'm just wondering if,
Well,
yeah,
I
if there's
mean,
other
it
places
only-
you'd see this effect, yeah.
Yeah, I mean, yeah, I guess I'm not sure what it would be calculated in this black hole scattering unless you're trying to find the quantum state on through the horizon. You wouldn't ever notice this. There's no energy involved in any of this. I mean, negligible, a
Well,
tiny
you
bit
get
of-
soft. Well, yeah, I'm just wondering if you
Yeah.
did a scattering problem in a short shield black hole, you would see these IR divergences like you see IR divergences in 4D
Yeah.
from soft photons. Yeah.
Yeah, you probably wouldn't see this sort of thing because the particles are all going far from the black hole. So
Oh.
you're not, this
Okay.
isn't a positional, a change in position staying near the black hole is producing the same sort of effect as a change in momentum is producing at null infinity in four-dimensional scattering.
Okay. Thanks.
More questions?
Thanks. Related to that question, in the four-dimensional case at Scry, of course, these memory effects are related to asymptotic symmetries, which are related to the perhaps reasonable, perhaps unreasonable ambition of celestial holography, whatever your opinion of that might be. But I'm wondering whether similarly here, part of the conversation in these talks has been about whether there is a kind of holographic dual closer into the action around black holes, for example, because you have something that looks like the asymptotic symmetries or memory effects that are there that have inspired the ambition of celestial holography in Minkowski space. Is there a kind of structure here that would lead us to clues to how to do a more local holography around the horizon of black holes that has been studied? I haven't caught up in recent developments on that.
Yeah. So, I mean, I think I more or less understand your question. I don't have any answer. I mean, there's nothing that sort of comes to mind that seems, I mean, you have analogs of super translations on the horizon and things like that, but I'm not aware of something that would help you go beyond what you already can see at null infinity. I mean, you have analogs, but at least nothing that comes to mind of analogies that would help you go further than you've gone at null infinity. And I'm not aware of any, other work that, I mean, I'm aware of work that has highlighted, what symmetry is on the horizon and things like that, but, I'm not aware of it suggesting. But maybe Ted is.
No, I have a question. You mentioned surface gravity once during your talk,
Yeah,
which was the relation between affine time and killing time.
yeah.
But I wondered when I first saw your work about what role the decay rate that the surface gravity indicates for other things might play in this. I think Sam Gralla wrote a paper
Yeah.
that kind of brought that out, but I don't really know what his conclusion was. Can you summarize, like, in what way is the final formula that you showed involving the surface gravity? Does that shed any intuition on the rate of decay of the coherence, the rate of decoherence?
Well, I mean, as you take the surface gravity to zero, this effect gets smaller. All of the estimates I gave were for Schwarzschild black hole and something, but if you, do extremal, go to extremal limits, then that was very nicely done by, in a paper by Grella and Way. And
so if you just say, okay, the rate of decay of coherence is the surface gravity times something, like, but you didn't write it that way. So what would be the something
Oh,
that you
well,
multiply it by? Or is it
I mean, the
linear?
thing is that, in the electromagnetic case, you don't actually, in addition to the affine killing time relationship, which works against you in terms of the decoherence effect, it also is the case that the electromagnetic field, the Coulomb field of the particle, does not penetrate into the black hole. So again, that in the Gralla and Way paper, I mean, they properly compute all this. I think Gralla refers to that as black hole Meissner effect. And so the effect is sort of shut off for that reason as well, at least in the electromagnetic case. I'm not totally sure off the top of my head about the gravitational case, but anyway, it is nicely done in that paper. I'm just not remembering the conclusions clearly and sharply.
Thank you.
Well, let's thank Bob again.